Today we'll get started with the inaugural tea time talk for this year from Professor Sutton. And yeah, I'll let him say some more words about how our tea time talks usually go. And yeah, the stage is yours, Rich.
Very good. Thank you, Abhishek. Welcome, everybody, to the first Tea Time Talk. The whole point of Tea Time Talks is to have a community and exchange ideas. Everyone is welcome to give a talk, and we want to trade ideas about what people are working on or things that they found interesting in the literature. We want it to be a fairly efficient way to communicate. So we try to keep to 20 minutes plus 10 for questions. And we're going to do it Monday through Thursday this year. Well, this summer, we'll see if that works out. Now, of course, we are communicating over a video conference now, and it's a little bit strange. Right now, I feel it's a little bit strange. I'm talking to my screen. I'm hoping you guys are all there. Yeah, I have to think most people here are from reinforcement learning and AI in Alberta, but there are some other people all over. I wonder if there's anyone here from Mila or from Vector. Anyone from Mila? Just raise your hand in the chat window, and maybe Abhishek will tell me how many people are raising their hand.
Yep, Katya is representing Vector. And yeah, I don't know if people have raised hands, but maybe there are a couple from Neela, from the people list that I can see.
Well, we didn't actually advertise very widely because this is the first time we're doing it. We don't know how it's going to work out exactly. Okay, well, let's get started. Today, I want to challenge you all to fully embrace approximation. I think we need to do it as part of what's happening in the world of AI. And so this is my question. Are you ready to fully embrace approximation? So if we look at machine intelligence today, much of it is driven by Moore's law, that increasing computer power, that's the backdrop to everything we do, and it drives the progress and drives the methods that are impactful. So the key phrase is methods that scale with computation are the most impactful. And that's partly explains why machine learning is so popular and so effective and having application success, and deep learning are having these successes. So scaling with computation, I'm saying it's new, slightly new. It's not the usual kind of scaling we talk about in computing science. The usual kind of scaling we talk about is scaling with problem size. So a bigger problem, you have, order the square of that, more computation, you needed to solve it exactly. That's the way we usually talk in computer science. But I want us to stop talking that way in some sense. I want us to talk about this alternative way, because now we're going to assume that the problem would never be solved exactly. It's impossible to solve. It's infinitely large. Understanding the world is infinitely large. We're never going to solve that exactly. So the new scaling is scaling with computation, the idea that with more computation, you get a better and better approximate answer. So let me say that one more time. We need methods that scale with increasing computation. Now, you may have heard me talk about this in terms of the bidder lesson. So I'm trying to actually extend the bidder lesson to one more step. The bidder lesson says we need methods that scale with computation, and so we really should be focusing on search and learning. But the second part of it is that we are scaling with increasing computation to better approximate answers. Key to it really is that it's approximation, because you get more computer power, you get a better approximation. And so we need to talk about approximation. Approximation is key. It's really why we can have scaling. We have to embrace approximation. And so have we been doing that? Well, we've been doing it pretty well. We've embraced function approximation. I think of the textbook that we finished a few years ago, and the second half of it is all about using function approximation. We've embraced that. We've embraced deep learning. We have deep reinforcement learning. Reinforcement learning has embraced, first of all, just learning from unprepared experience. That's something that enables you to scale with more and more computation, more and more interaction with the world. You can get better and better answers. So it's just the whole basic reinforcement learning idea of learning from experience. Unprepared experience is part of paying attention to how you scale with computation, how you get better and better approximations. Modern reinforcement learning has embraced search, of course, particularly Monte Carlo tree search, and we've embraced the idea of experience replay, and to some extent we've talked about planning. So all these things scale with computational resources, and they're part of modern reinforcement learning. So it's not that we haven't done anything at all, but we haven't really fully embraced it. That's my argument. Reinforcement learning has held back, hasn't fully embraced approximation. So why is that? What do I mean by that? Well, reinforcement learning is grounded in finite MDP, Markov decision processes, and in tabular methods for solving those things. You know, when you learn the beginnings of reinforcement learning, it's all about, you know, Q learning and tables, and then we try to extend it, but it's really colored by the fact that we started tabular. So to really abandon that starting point, finite MDPs, it does, I think, challenge us psychologically and requires strong discipline. So I'm going to try to do that, challenge you here and encourage you to have that discipline. So the reason it challenges us is that fully embracing approximation, we lose so much. First of all, we lose all the stuff about discounted reward and all the theory that's built on that. So probably many of you have heard me rant and rail against discounting and gamma and how we should avoid it. The reason for that is all because of the shift to function approximation. Once you're in function approximation, really the discounted formulation of the problem no longer makes sense. You can't really pursue it. Your optimal policy is not going to be in the class of your function approximator, and you really can't do discounted reward. Now, I don't want to dwell over on that. It always takes a while for people to understand that. But it's an example of how we haven't really fully embraced function approximation. So the second one that's pretty well known is that we lose Bellman errors. This is also discussed in the textbook, that once you have function approximation, you can't really tell from experience what the Bellman error is. You never can. It's just the information is not in the experiential data. So, and yet you will still find many papers that tell you we have a learning algorithm and we can learn to minimize the Bellman error, but it's impossible. It just follows from the fact that it's not available in the experience. Somewhat less often discussed, but even more fundamental, is we lose the Markov state. Our state is no longer a complete summary, or the thing that the agents are going to use as if it is state is not the whole state. And thus, we really can't talk about transition probabilities. You can't talk about expectations. And some of the things that we talk about most of all in reinforcement learning are the value functions. Well, as you know, those are expectations of returns. And so we really lose all of our true value functions. So it seems like we're losing a lot, and like it's a bad trade-off, maybe. It seems bad, okay, to lose all this stuff that has been our grounding theory, okay? So how have we dealt? How has reinforcement learning dealt with this loss? Well, I refer back to the famous 5 stages of grieving. I don't know if we've gone through all of these steps, but certainly the first one is really prominent. There's a lot of denial. So there are many people out there who say, who for example, the discounting thing. People are still using discounting with function approximation, and it really doesn't make sense. So people are just denying that that's a need, in my opinion. And discounting, I don't have really what do they say? A dog in that race, a horse in that race. I didn't generate any alternatives to discounting. The alternatives have been known for a long time. Average reward, and it was like 20 years ago. Someone shared with me, made it apparent to me, I think it was Sham Kakade, that it doesn't really make sense to talk about discounted reward once you have function approximation. And so he just doesn't do it, and he, looks askance at people who try to do it. And anyway, so we've denied that. Lots of people deny the Bellman error. I don't know, you remember a couple of years ago, we had someone come through and tell us that they found a new way to through learning, minimize the Bellman error. It can't be done. It's not available in data. A lot of denial, and then maybe we bargain, well, I'll do this, but I won't do that. I don't want us to get, I don't see too much anger, and I hope we don't get depressed just because things are harder. What I want you to get to is all the way to acceptance, accept these changes in our basic mathematics and theory, and then all kinds of interesting opportunities open up. So I'll try to tell you that today and the rest of the talk. So what's the usual way we deal with approximation and reinforcement learning? Well, we have this mapping phi, and it maps world states. I'm going to call it world states. It's really environment states that you can't know, that are unknown, but somehow they're turned into feature vectors. So as you see, I don't know, I wonder if you guys can see, you can probably see my cursor. Abhishek will tell me if you guys can't. And so, good. So we take in the state at time t, pass it through the feature function, we get the feature at time t, and that's in a real vector, say, in d-dimensional space, and where d is much smaller than the size of the state space, much smaller. And then all of our agent operations can only use the feature vector. So there is sort of reference to the environmental state, which is unknowable and unknown, and actually we actually have to work with the feature vector. So when we talk about an approximate value function using weights W for state S, really we convert S into a feature vector, and the feature vector is used to get the approximate value. Okay, so note that this phi is not going to be Markov. It doesn't summarize all the past. What happens next will depend not only on the feature vector, but on the past sequence of feature vectors and actions. So here's an example of that problem. You might be tempted, and people are tempted, I was tempted. I recently wrote a paper where we proposed doing this, and I now see that it's wrong. We might be tempted to talk about the probability that the next feature vector has some value, given that the current feature vector has some value. But that is not really defined as a probability. It doesn't go through. And I'd like to just spend a moment and do this example with y'all. So here's a Markov reward process, which just means it's a Markov decision process without any decisions, without any actions, or equivalently with a single action. So, and it's all deterministic. So you go around this cycle, and you would see, and what I've labeled here in blue are I've given the feature vectors names. So there's one feature vector that's A, and another feature vector that's B. And in these two states, you get the same feature vector, and these two states, you get the same feature vector. So that's clearly a case of this feature mapping. But now if you look at what will the data look like? Well, you'll see A, and then B, and then B, and then A, and then A, and B, and B, like is shown here in blue. That's what you will see. And when you comes to this probability, well, you see that there is no probability. When your feature vector is A, you might get another A, or you might get a B. But it's not probability. It's, in fact, everything is deterministic. Everything is deterministic. These are not probabilities. If you approximate them as probabilities and model the world that way, you'll predict different behavior. So this probability doesn't exist, basically. You can't do that. Thinking a little bit further, this first line is just repeated from before for you to remember. Now, how many feature vectors are there? Well, there's more than D. D is just the number of features. We're in an R to the D space. In principle, phi might match all of the different states to different feature vectors. So in that case, we would have the number of states, different feature vectors. And because of this, you cannot, none of the agent processes are allowed, should be considered to be allowed to treat feature vectors as individuals in any way. You'd have to process them parametrically. So it's another reason why you can't do this, because if you were tried to do this, even if it made sense, you would end up storing different things for each feature vector. Right? If feature vector is phi, you'd store one prediction was another 5, make another prediction. And so you'd end up with, again, making way too many, storing way too many things. You'd be storing things on the order of the number of states rather than the number of features. And you can't do that. And in addition, it would depend on behavior policy. That's like the least problem. Okay. How am I doing here? Can't take too long. So fully embracing approximation, what does it mean? What does it mean to do it fully? Well, obviously, as we just said, you can't store things for individual states. And similarly, as we just said, you can't do things for individual feature vectors. You can't store them distinctly. And the agent you work with, the state the agent works with has to be will not be Markov. So then, in addition, it means you'll never converge to the exact correct anything, even in the limit. So if you see a paper that claims to be about function approximation, they say, oh, I can make all these approximations, and then they say one more. They say, oh, and in the limit, I get the exactly correct thing. Right then, when they say that, you know they're not really talking about approximation. They're not doing genuine approximation because they have a guarantee that you'll converge to the right thing. It's a totally different setting, and it's a totally different theory. They're not really embracing the idea of approximation. Also, and related, the world is much bigger than the agent. The world is much more complex than the agent. That's why the agent cannot understand it completely, cannot converge exactly to anything. So now notice this sort of a challenge, this thing that I'm saying. The world is much bigger than the agent. And yet, at the very beginning, I've been talking about the agent's computational complexity is growing exponentially. So even though it grows exponentially, and it's going to be huge, we're never going to be more complex than the world. The world is infinitely complex. The world's complexity and your need to understand it will grow with your length of your experience and with the whole world. Okay, and then, as I'll talk to in a minute, this will mean that even the best approximations will change over time. Let's go ahead. Here's my picture I like to show to say the world, here's the world, and it's much more complex than my agent because, well, like the world contains all these other agents, in addition to all the other planets and continents and galaxies. The world is much more complicated than you are. Now, if we accept approximation, so now I want to talk about what happens if we fully embrace it. And I'm going to go through 4 steps and talk about the problems and the techniques and the opportunities, a little bit of math, tiny bit of math. So what if we embrace approximation, it's okay, we can still do things. Everything is just a little bit different, and perhaps it's better. Certainly it's more real. So the first obvious thing to do is to replace things like the transition probabilities and expectations by a function approximator who has a loss. And as I said, there aren't true value functions because those are expectations, and they're a function of the real or the world state. But you can have approximations with a loss. And the trick is to deal with the return error. So you can define for a fixed policy the mean square return error. This is the mean square return error. It takes a weight vector, and you can talk about the difference between the approximator, estimated value of a state, and the return at that time. So at that time, you know, every moment goes by, you're going to have a return. Return is just a random variable, sum of the future rewards, and you compare that. You also have at each time an actual guess, an estimate of its value, so you can get those things. You can square them. You can use this loss. Okay, that's step 1. Step 2 is we have to move beyond discounting. So you have to move to average reward and the reward rate. And so just notice that this is kind of elegant to talk about the reward rate, what's the average reward and an average step. That's the rate at which you're gathering reward. And it's just a scalar. Every policy will have a scalar. And you can rank policies according to that scalar. If they get lots of reward, then they're good, and they're a better policy than a different policy that gets less its reward at a lower rate. So this is something that you're not able to do with discounting. You can't rank arbitrary policies. Policies don't convert to a number. They just convert to value functions, and they cannot be, arbitrary policies cannot be compared by their value functions. Because one policy will be better in one state, a different policy will be better in a different state. There's not a single number to compare them. So as I said, we can do this. This is less well developed, but we can do it if we just pay attention. So a couple students here, Yiwan and Abhishek Naik, have just made some good progress on learning algorithms in our NIPS submission, and I'm sure we'll hear about that in the coming weeks. And step 3 is we want to go beyond the feature function. Okay, instead of this unknowable function accessing an unknowable world state, instead you have a known function, the state update function, and it will operate on known experience, and it'll have an objective, and so it's just much more to work with. So the state update function, it's you, and it takes in a state, an action, and an observation. You have observations instead of states, making up the stream of experience, and gives you your new state. This is just a better way to get the non-Markov state, and we're doing a lot of work in this context here. And what I call the agent state research group is working on within this better way to deal with non-Markov state. Now, this last one is perhaps the most interesting. So see if you can, and I have to just sketch it, see if you can follow the thread. Basically, I'm saying that once you embrace approximation, you accept that, then you have this opportunity because you move from converging way of thinking to a tracking way of thinking. So the logic is approximation means accepting that the world is big and you can't get anything exactly right. So what? What do? You could converge to the best approximation, the best static approximate solution, balancing all the errors. But there's an alternative. You could track the current best approximation. Instead of like getting the one that's best average of everything, you try to do the best you can right now, get the best approximation now. And it's surprising, but if you do this, you can actually do better. And maybe I think it's going to be much better. Dave Silver and Anna Koop, we had a paper a while ago about showing that you could do this. Dave, this is examples in Computer Go. Tracking can actually be better. And so if you're tracking, that means you're learning and relearning continually, online. You can't do offline things. It's like an endless sequence of related learning problems, but they're all from the same problem. There's really only one problem. You're just encountering different parts of the state space at different times. And so you have to learn and relearn. And if this is true, then approximation itself provides a new basis, a new rationale for the idea of online learning, for the idea of meta learning, for the idea of how you could learn to generalize, and how you could learn what good representations are, because you're seeing this, you have this online repeated continual learning problem that you're having to address all the time, and you can find ways to meta learn and learn representations that enable you to generalize better. So I think this is a real opportunity. Okay, so in conclusion, Zeigarnik approximation is the key to future advances in machine learning, as it's been the key to where we are now. And RLAI, as the premier research institution, we should be leading the advances in approaches to reinforcement learning that use as fully as possible the power of approximation. It seems like a difficult challenge, but it's necessary, and it will yield great dividends and opportunities if we fully embrace it. So fully embracing approximation is on the critical path to the future of machine intelligence. Thank you all very much for listening, and if I can, I'll try to take questions now.
Rich, I have a question which is required in context. I put a URL in the chat bot, and the URL is to the 78 best approximation textbooks, approximation algorithm textbooks. And the only reason I put that there is that I'm on your side about approximation because I think that the world is its own best representation, and you need to be disciplined about approaching what your approximation is. Now, I have a luxury and the curse of being a what amounts to a postdoc in Guahi Lin's approximate algorithms group. So I end up over and over again asking questions and rewriting things and trying to explain them. The key there is that the computational complexity to provide an estimate for an approximation algorithm is proving bounds on something that you can declare to be a measure, and that's what's missing when you that's what's missing at the head end of what I think you're doing now. So a key will be to say
well, Randy, let's not say it's missing. That's what's different. Both the classical methods and what
yeah.
the method you just described are about how can you get to a level of performance and how much computation it requires.
Yeah, and
well, really, yeah,
I agree. And so the key for what you're proposing, I think, lies in that measure of how confident we are about blending the techniques we have, like the loss function, how confident we are about what those tell us about whether or not we're getting closer approximations. As soon as you get that, you can apply all of that incredible work in approximation algorithms, because they will tell you if you have an approximation that is this shape, you can improve and tighten the bounds on identifying it. So that's a great promise if you can do what you said. So that's just what I wanted to add and note.
Thank you, Randy.
Yeah, Professor Matt had a question in the chat. If you can't see it, I can read it out.
Yeah, I was just saying that this sounds great. Suppose I'm completely on board. Does this mean I should stop submitting proofs that only apply in, say, the tabular case? Or is that still important and interesting?
Well, speaking as someone who just submitted a paper with a proof for the tabular case, I have to admit that it has a good role. It has a role for it. That was Abhishek and Yi and I have our paper on average reward learning and planning, and the state of the art there is to get tabular methods proven. But we want to, obviously, we're doing this discounted case because we really want to move to the case with proper full approximation. So just be sure you know where you're going and you're not targeting someplace that's not going to contribute to where we want to get to. Brendan, you have a question? If you have to unmute. Yeah.
Yeah, I was just wondering, like, if we are abandoning a idea of there being some underlying truth that we can learn, then what sort of statements can we make mathematically, for instance, if we don't even have hypothetical access to that underlying truth?
Well, there is truth, but we're not going to approximate it exactly. We're not going to reach it exactly. There is truth. So among the space of approximate solutions, some of them will match reality better than others. We absolutely have truth. We just have to realize our own limitations.
So, for example, prediction as knowledge should be supported by approximation, right?
Yeah, right. And the goal, the best we can do, the best approximation with our system will not solely be a property of the world. It will be a property of the world and us together. So that's why it's okay that the world doesn't define an ideal function that we need to be. We have to define instead the best function we can get given our limitations.
So Rich,
good question.
Let me follow up with that. Like I feel like Brendan's almost asking the question, yeah, this is Mike, by the way, about whether we have to abandon theory. And let me say what I want to say with theory. So you sort of said we had to abandon parts of it in the sense that we're not going to make claims about our algorithms converge to optimal this. But there can be theory that says that, you know, we find the best within a class. and the best at an objective that maybe our agents can actually measure, so that this is well defined and it's plausible. Is that theory, do you think it's interesting, or do you think that no, we really should just to fully embrace it, we have to abandon theory too?
Well, thank you, Michael. I'm glad you get to have this opportunity to correct that possible misapprehension. I'm not claiming that theory is unimportant. Just the theory that's entirely tabular is not so important. Theory is actually, really I want to challenge everyone to develop the new theory that's needed for the proper case, for the approximate case. I think we need a lot of theory.
In fact, what Michael just said is related to how the degree to which you can achieve consensus with your tabular methods, since we're all approximating the world in a different way. There's another way of thinking about it too.
Cool. Anyone else have questions out there?
Yeah, we can take one more and then we have to close. Hi, Rich. This is Roshan.
Oh, sorry. I think Martha
Roshan.
had a question beforehand as well on the chat. Abhishek, if you're moderating, I think Martha's got one in the queue.
Okay, sure. I can ask my question quickly, but my cat might be meowing in the background. Anyway, I just want to understand, you made a bold statement that the probabilities are not defined, and I feel like I heard you maybe say the expectations are also not defined, and I didn't follow that, what seems like very key argument. Could you just explain what you mean?
Yeah, I'm sorry not to stop on those things. It's really quite worthwhile to go through them carefully and see why there can't be probabilities and there can't be expectations. It's because you don't have a Markov state. That one example is somewhat useful. You can see that there are no probabilities there, and if you tried to construct them from the data, you would get things that aren't probabilities. Why can't you have expectations? Well, an expectation is, I expect, like the return to be given something, and normally it's given the state, and that given the state only makes sense when it's Markov. If it's just given the state, and you want to pick out all the times when that, if it's just given a feature vector, then it doesn't really work for all the reasons I went through today. Very quickly, I think it just takes more time. So the way I expressed it, this is my hope, is that you guys would just go home and say, Rich says you can't have expectations. The expectations don't make sense. You can't approximate them, and they don't really even make sense. And because that's a really clear statement, at least it's maybe not wise clear, but it's a clear statement. It's a challenging statement, and you need to think it through yourself and see that that's true. Or maybe it's a claim, I guess. But I think it's just true.
Yeah, we do have some discussion going on in the chat, but I think we'll have to close for today. We can continue discussing these things in the meetings and some meetups like this. I would also like to say that on Fridays we'll have like a open social session where we just come in and talk about things, life in general. And so feel free to come to that and discuss all sorts of things. And I would like to thank all the 120 plus people who joined in today. That's the most we've ever had in Tea Time Talks, and I guess that's one benefit of virtual talks. And
bigger rooms.
And finally, I would like to make a plug for tomorrow, which will have our very own Csaba Sapsari will be giving the talk. I hope to see you all tomorrow.
See you.
Bye-bye. Thank you.
Bye, everybody.